Okay, here we are in question 17. Question 17 is on a refraction of light. And what are we given here? We are told that figure 10 shows a ray of light traveling from glass to air. Determine the critical angle of the glass-air interface. Critical angle. What is critical angle? And when do we talk about critical angle? We talk about critical angle when the ray is moving from an optically denser medium into an optically less dense medium. For example, in this case, you can see that the ray is moving from glass, which is optically denser compared to air. So it's moving from a material with a higher optical density to a material with lower optical density. So you expect the angle of refraction in air to be greater than the angle of incidence in glass. And remember, the angle of incidence is the angle between the normal and the incident ray. And you can see over here that that angle is 42 degrees. This is this angle that we are talking about. The angle of refraction is found in air, and it is the angle between the normal and the refracted ray. And this is the refracted ray. The next thing is this. You realize that the angle of refraction in air is 90 degrees. It is at that point that we realize that actually 42 degrees is the critical angle. Critical angle is the angle of incidence. The angle of incidence in the optically denser medium, for which the angle of refraction in the optically less dense medium is 90 degrees. And you can see those conditions have been fulfilled. And that is how you identify 42 degrees as the critical angle. So you'll just say here that the critical angle C is 42 degrees. And it is just as simple as that. There was no calculations involved. Then we are asked to calculate the refractive index of glass. So we remember that we can be able to calculate the refractive index of that optically denser medium if we know the critical angle. So that's it. Critical refractive index of glass is 1 over sine C, where C is the critical angle of that particular medium. So we're going to say this one is 1 over sine of 42 degrees. Let's see what that gives us. 1 divided by sine of 42. And I get 1.49447. We could say it is approximately 1.5. 1.5. And that is how you work out that part. Let's look at part 2. We are given that a piece of metal is embedded at the center of an ice block 14 centimeters from the surface of the ice. So there is this ice block here. There is the ice block. There is the surface of the ice block, and we have this piece of metal inside here. Inside there. We are told that it is embedded at 15 centimeters from the surface of the ice. So this is how far it is. 15 centimeters. What else are we given? Given that the refractive index of ice is 1.32, determine how far from the surface of the ice the metal appears to be. So if we were to look at that material from above here, where will it appear to be? it will appear to be near us. It will appear to be somewhere around here. So how much will that depth be? How far will it be from the surface? Now here we are talking about the real and apparent depth. This is the real depth. 15 centimeters is the actual depth of that metal from the surface of this material, while the apparent depth is how far it appears to be. The refractive index of this material, N, is given by the real depth, depth over the apparent depth. So here we have got the apparent depth. The apparent depth is the depth that the object appears to be, how far it appears to be from the surface. So the real is 15, while the apparent is D, but the refractive index is 1.32. And we see that the apparent depth is 15 divided by 1.32. What does that give us? So we get 15 divided by 1.32, and I get 11.36 centimeters. You can say 11.4 centimeters approximately. So observe how they have described real depth and the apparent depth, because that skill is required. And then how you identify that you've got to use this concept of real depth over the apparent depth to determine the refractive index of the material. So let's go on to the next question. This is about refraction. It's about lenses, and lenses work on a refraction of light. Over here we've got a diverging lens. Figure 11 shows two rays of incidence on a diverging lens. Complete the ray diagram to show the path of the rays after passing through the lens. Number one, you observe that these two rays are parallel to each other, and you observe that one of them is passing through the optical center of that particular lens. The optical center of that particular lens. What is it that we expect? If you put your ruler against on this line like this, you will also observe that this ray passes through this F. In the actual question paper, you find that they had made these distances different. So this was a little bit shorter than this one here, the focal length. That one is possible because the curvature of the two surfaces of the lens need not be the same. But at this level, we usually study lenses which are of uniform shape. That is, if we are talking about a diverging lens, for example, the focal length on one side should be equal to the focal length on the other side. So I don't know whether that was intentional or, by mistake. So I just drew this diagram, making the two focal lengths to be the same. And when I looked at that diagram properly, I found that this ray actually passes through F. A ray, actually, it appears to pass through F. It actually does not pass through F. If it was a convex lens, it would appear to pass through. It would pass through F. But for a diverging lens, it appears to pass through F. So what would happen to this ray? First of all, let's agree that this one will pass on undeviated. It will not bend at all. It will just pass on straight. But this one, since it appears to pass through F, it will be refracted parallel to the principal axis. And using this refracted ray and this refracted ray, I would extrapolate this one backwards and see that they met somewhere around here. And this is the diagram that I got. So this one, because it appears to pass through here, then it would be refracted parallel to the axis. When I extrapolate it backwards like this, then they meet somewhere around here. And this would be the focal plane. Now, the fact that these two rays are parallel to each other means that they would appear to meet at the focal plane. The focal plane. So, and if you draw this diagram accurately, you'll find that wherever they appear to meet will be somewhere along this vertical line here, which identifies the focal plane of this lens. How about if that lens was somewhere else, but still parallel to this? What would happen? So I also included a ray here, which is parallel to these two, just to show that it will be refracted in such a way that they meet at the focal plane. So remember, this ray need not necessarily pass through this F, but provided it is parallel to the one which passes through the center here, the two are parallel, they are going to diverge. And they will diverge as if they appear to come from the focal plane. Focal plane. The only point they would appear to meet at the principal focus is if they were parallel and the two rays are parallel and they are also parallel to the axis. That is when they will appear to meet somewhere here. So I thought of adding this green ray here so that I can show you what would happen if situations change. And let's go to part D, where we are asked to state two differences between the human eye and a camera. We are also asked to name the part of the eye that enables the lens to focus images of the objects of different distances. First of all, let's look at the human eye and the camera. They are quite comparable. So we are asked to compare the differences between the human eye and the camera lens, this lens and this lens. Of course, both of them are convex. All those are similarities. Let's look at the differences. What would be the differences between them? The differences are as follows. The focal length of the eye lens is variable, while the focal length of the camera lens is fixed. Now, how is that possible to vary the focal length of the human convex lens? We make use of the ciliary muscles, which when they contract, they make the lens thick and therefore reduce the focal length. That is when they relax. When they contract, they make the lens to be thin and the focal length increases. Number two, the camera with zoom lenses has variable image distance. You are able to vary the image distance, especially when it has got a zoom lens, while the eye has a constant image distance. You're not able to vary the image distance in the eye. I've given a third difference. Only one photograph can be taken at a time when the shutter opens, but the eye is always open to form constant changing pictures. So those are some of the differences that you would be able to quote. Only two were required. So I've given you three so that you can be able to understand the third one. And of course, the name of the part of the eye that enables the lens to focus images of the objects at different distances is, of course, the ciliary muscles. The ciliary muscles. If we go back there, you'll be able to see the ciliary muscles. These are the ciliary muscles. When they contract, they make the lens to be thin, and that is going to vary the focal length of the lens. When they relax, they make it thick, and it's going to shorten the focal length. So that is it about question 17. Let's move over to question 18.